this integral, his work with the parabola, and he knew that it came down to a certain series, that ultimately you were interested in this area, and it was natural to break it up into little rectangles, and then if you analyzed all these rectangles, eventually you had to add them up, and you got a certain series that you had to sum. And this series is essentially the series of all the squares up to k squared. And Archimedes knew what that series summed to. It sums to k times k plus 1 times 2k plus 1 all over 6, which is roughly k cubed over 3 plus lower order terms. So if we ignore the terms lower in degree k, the top term is k cubed over 3, and that's what really ends up driving the integral to be 1/3. Well, the 17th century people also realized this, that it was important to sum this kind of sum, and that if for higher powers of n, you needed to sum or to get some control over sums like this with higher powers. For example, things like 1 plus cubed plus 2 cubed plus 3 cubed and so on up to k cubed. This is another interesting sum, which is a lot like, turns out it's exactly the same as the sum 1 plus 2 plus all the way up to k, all squared. It's a rather remarkable fact. And 1 plus 2 plus all the way up to k is the same as k times k plus 1 over 2. So this one is all of this squared. And if we just take the highest order terms, we're getting k to the 4th over 4, and then plus lower order terms. Again, we can see that the integral being 1/4 appearing from that sum. Well, this sum is a little bit more challenging as these exponents get bigger, and it becomes a little bit tricky to find closed form expressions for these things. It was eventually done, but a little bit only later. But people found indirect ways of calculating these integrals, and it was Cavalieri who first established this formula. Cavalieri established this formula not by using such a series, but rather by some tricky transformation arguments involving the actual curves. But he wasn't able to prove it for all n. He was only able to prove it for n equals 1 up to 9. So he had separate argument for each degree. And then later on, Fermat and Descartes and Roberval came along and established this result in generality for general n. Cavalieri is also known for kind of a principle. So just to give a very simple example of it, suppose that we have a triangle here with some base d, and we have another triangle over here with also a base d, but it's sort of slightly different. So these heights are the same. Then the way Cavalieri thought about an area like this was as a lot of little infinitesimally thin line segments all stacked together. And by thinking this way, he could compare all the line segments stacked here with the ones stacked there. It's not too hard, for example, in this case, to see that if you draw a line parallel to the base here, that this line segment here is necessarily the same length as that line segment, just by similar triangles. So the fact that this segment was the same as this segment, and that was true for any parallel line, allowed Cavalieri to conclude that in such a situation, the area of this must be equal to the area of this, because all the little cross sections are the same. And he applied this kind of reasoning to more fancy things. In particular, he was able to calculate the volume of a sphere, going back also to Archimedes, in a nicer, more obvious way than Archimedes had done. And it was a powerful idea, and it turns out that once people discovered Archimedes' method, which was only discovered in the beginning of the 20th century, that this was not too far from Archimedes' point of view as well. He also thought of dividing things up into lots of infinitesimal little strips. Okay, so once people had this fundamental formula here for integer values of n, typically, first n equals 1, 2, 3, 4, and so on. They also thought about variance. For example, what about fractional powers? So suppose we're interested in the integral from 0 to 1 of the square root of x dx. That's the case of our formula where n is equal to 1/2. Well, it turns out that the formula still works. So with n equals 1/2, we would get 1 over 1/2 plus 1, which is 2/3. And one way of reasoning, of establishing this, is to think geometrically. So here is 0 and 1 and 1. And to start off with the function y equals x squared. The function y equals x squared, well, we know what the area under that is because that's the formula that we already know. So we know that this is 1/3. And then you realize that when you're looking at the square root of x, the picture is a lot the same, except that instead of going up like this, the square root function looks like this. So there's y equals square root of x. In fact, it's just the reflection of this one along this diagonal. So if this one is equal to 1/3, that means that this must be equal to 1/3 by symmetry. And so this one, because the whole square is 1, this one has to be 2/3. So you could then find the integrals of fractional powers in this rather direct geometrical way. So this extends the formula, extends our basic result to fractional powers. John Wallis discovered some lovely formulas due to pi. So pi, of course, had been a source of fascination to mathematicians for a long time. We've seen Archimedes think about pi. We've seen with the Arab mathematicians, the Hindus, the Chinese. Everybody was interested in what is pi, what's a good formula for it, what's a good approximation for it. So Wallis found a rather remarkable formula as an infinite product, very unusual kind of thing. So it says pi by 4 is 2/3 times 4/3 times 4/5 times 6/5 times 6/7, and you keep going. So after this, the numerators are all even numbers in pairs, 4, 6, 8, 10, and the denominators are all the odd numbers in pairs, 2 3s, 2 5s, 2 7s, and so on. And as you get closer and further and further on, these numbers approach 1. So what happens if you take products? Well, you start stabilizing towards some particular value. So if you compute the first 10 values, you get an approximation to pi, and if you compute the first 20 values, you get a better approximation, and so on. It was a rather remarkable formula at the time. Another formula that was discovered was a continued fraction formula for not pi over 4, but actually the reciprocal of pi over 4. And that continued fraction was this: 1 plus 1 squared over 2 plus 3 squared over 2 plus 5 squared over 2 plus 7 squared over 2 plus, and so on. It's not exactly the kind of continued fraction we've talked about earlier. It's a kind of a modified continued fractions where these numerators that are appearing here are allowed to be something different from 1. But it's still very regular. All 2's here, and here just all the odd numbers. The actual continued fraction for pi is very irregular, and it's very hard to know what the pattern is. Here the pattern is completely given, and so we know exactly how it continues, and we get this really remarkable formula. In fact, it was a sort of a glorious age. People were discovering these formulas, and they were all very excited by these formulas that they discovered, and they would exchange letters. And I think it was a time of they really knew that they were in a great new world, and there was lots of, they had these tools to discover these fabulous new things. I probably should also mention another formula for pi, which 1 minus 1/3 plus 1/5 minus 1/7, and so on, that you're probably all familiar with. Okay, so now we come to the two main figures, to Newton and Gregory. Not Newton and Leibniz. Gregory is also important, but so Newton, brilliant physicist, great mathematician, rather exotic character who later on in his life became interested in all kinds of religious things and was master of the London Mint for many years. And certainly made a name for himself with his great work, the Principia, which laid out laws of motion. We'll talk more about that. That was absolutely fundamental work in modern physics, laying the groundwork really for the modern technological age. But he also made important contributions to mathematics, and in particular to calculus. He was, with Leibniz, he's usually considered one of the co-inventors or co-discoverers of calculus. Now, Newton's thinking was characterized by certain ideas. So I would say that, first of all, he had a very dynamic view of things. And by that I mean he was a physicist, okay? And he thought about things moving. So for him, time was somehow behind all kinds of functions. When you had a function, it was really expressing the movement of something with respect to time. So he was very interested in the interpretations having to do with velocity and acceleration and distance, because that naturally fitted with his work in physics. The other very important characteristic is that he had a love of series. And he was really the originator of what are now called power series, which are the main tool for analysis. And I'll give you a quote from Newton's from Stilwell. Newton in 1671, he writes the following: "Since the operations of computing in numbers and with variables are closely similar, I am amazed that it has occurred to no one, if you accept N. Mercator with his quadrature of the hyperbola, to fit the doctrine recently established for decimal numbers in similar fashion to variables, especially since the way is then open to more striking consequences. For since this doctrine in species has the same relation to algebra that the doctrine in decimal numbers has to common arithmetic, its operations of addition, subtraction, multiplication, division, and root extraction may be easily learnt from the latters. What Newton is referring to here is that not too long ago, people had become familiar with the Hindu Arabic number system, and they knew that it was nice to deal with infinite decimals, or at least decimals that carry on. For example, pi. Okay, and I remind you what this really means. This is 3 plus 1 times 1/10 plus 4 times 1/10 squared plus 1 times 1/10 cubed plus 5 times 1/10 to the 4th, and so on. And Newton said, all right, well, what's really going on here? When we're learning to do arithmetic with these decimals, what we're really doing is we're learning to deal with powers of 1/10. That's what it amounts to. And what's so special about 1/10? We could just as well consider, so slightly more generally, said, why don't we consider things in the form a0 plus a1x plus a2x squared plus a3x cubed, and so on, where the x is not necessarily 1/10, but perhaps something else, or maybe just a variable. And his point that he's making here is that if you know how to do arithmetic with these kind of decimals, then you automatically know how to do arithmetic with these kinds of things, because you multiply them in exactly essentially the same way as you multiply decimals. You add them, you divide them the same way. He even says that you can extract roots, like a square root, in the same kind of way. So for Newton, something like this was really an infinite polynomial. And to him, this was what a function was. A function was an infinite polynomial. So there were polynomials, and then you went further, and then you got infinite polynomials, which are functions. And that's basically what analysis is about. So as far as Newton was concerned, the formulas for derivatives and the formulas for integrals really just amounted to two formulas. All what you really needed to know was that the derivative of x to the n is nx to the n minus 1, and that the integral of x to the n is x to the n plus 1 over n plus 1. And then you could differentiate and integrate any series whatsoever. You didn't need to know really anything any more than that. But you had to have some skill with the algebra of these infinite polynomials, and Newton had quite some considerable skill with them. And I think it's really the introduction of these kind of series into mathematics that really distinguishes this century and opens up so many new directions. So, for example, some examples of series that are important. Well, perhaps the most important series is the geometric series, which tells us that 1 over 1 minus x is 1 plus x squared plus x cubed, and so on. Now, strictly speaking, these days we would say, all right, this is only valid when x is less than 1. Otherwise, it doesn't converge. But in those days, this kind of fussing around was not necessary. We just talked about this thing as a function, and we didn't worry too much about its values at particular points and whether they converged or not. So, for example, if you want 1 over 1 plus x, it's a small modification. You just replace x with minus x, and you get an alternating series like this. And then if you want to integrate, let's say we integrate 1 over 1 plus t dt from 0 to x, well, then we're basically just integrating this thing here. 1 minus t plus t squared minus t cubed, and so on, dt. And so we can apply the fact that we know what the integral of any one power is, and then we just get x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, and so on. And this was the quadrature of the hyperbola that he's referring to, of Mercator. This is a very important problem because it fills a gap that our basic formula left out. So our basic formula was integral of x to the n dx from, say, 0 to 1 is 1 over n plus 1. But there's obviously a problem if n is equal to minus 1. Okay. So for n equals minus 1, there is a problem. N equals minus 1 is the function 1 over x. So here's the function 1 over x. It goes through 1, 1. There's y equals 1 over x. Okay, so integrating the area under here, we don't have a formula for it. They didn't have a formula for it, but Mercator's formula, this one here, really provides an answer. And although it looks a little bit different because instead of having 1 on t, we have 1 over 1 plus t, the effect of which is to shift it by 1 to the left. So if I shift this 1 to the left, I get this. Then we'll have an asymptote here, and it will look like this. Okay, so in yellow here, this is the function y equals 1 over 1 plus x. And this now is a nice function at 0. It's right there. And we can then try to integrate it. And that's exactly what this formula is doing. It's giving us the integral of this function, which is a new function that people hadn't seen before. Obviously, it has to start out at 0 and kind of goes up like that. You can extend the integral by going to negative values as well, and you get negative values here. And what is this function? Well, these days, it's what we call log or ln of 1 plus x. And if we translated it over 1, I'll just do it here. Coming down like that. That would be just to translate this thing over. That would be log of x. So this can be taken as the definition of what the log function is. It's what you get when you try to integrate the one case that the Cavalieri's formula doesn't work for. You get a new function, you have to throw it into your tool chest, and of course that enriches the subject quite a lot, because then the inverse function is the exponential and so on. And this is the kind of thing that Newton loved doing. He would say things like, okay, so let's call this y. So let's say y equals x, or x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. Can we write x as a function of y? How do you invert this? How do you write x as a function of y? Well, what he did is a rather clever thing. He said, well, what we'll do is we'll suppose that x is also a power series in y, but the coefficients we don't know yet. So we'll let them be unknowns, perhaps a0 plus a1y plus a2y squared, and so on. And then we'll plug that into here. Now we've got a lot of big algebra to do because we have to take that thing there, and then we have to square it, and we have to cube it, and we have to take the 4th power and then combine them all and then see what we get. And then we're going to compare coefficients. On the left-hand side, we just have y. On the right-hand side, we have this whole bunch of stuff. With any luck, we can deduce what these values must be. And in fact, it's a great exercise. You can do that. What he found is that you get a series which is 1 plus y squared over 2 factorial plus y cubed over 3 factorial, and so on. Now, I may not have done that quite correctly because this is ln of 1 plus x. Yeah, okay, that's not quite right. If y equals ln of 1 plus x, then what should x be? Then 1 plus x should be equal to e to the y. And so x should be equal to e to the y minus 1. So the series that he would actually have gotten wouldn't have this 1 here. That's the series for e to the y that I was starting to write there. That's better. Okay, so we now call that, well, without the 1, that's e to the y minus 1. Because I happen to have inverted this one here. So in high schools these days, you often start with the exponential function. You define the exponential function through some geometrical series, and then you take the inverse function to find the log. But it's mathematically more natural, as the 17th century mathematicians realized, to define the log first. The log is essentially coming from integrating 1 over x, and then inverting the log function to get the exponential. Well, Newton was an expert at this kind of thing, and he did lots of other things like that. And one of the most important things that he thought about was the binomial series, which was a key tool in other things. And after the geometrical series, it's probably the next most important series, so the binomial series. Well, you're probably familiar with expansion of 1 plus a to the n as 1 plus n choose 1 times a plus n choose 2 times a squared, and so on, up to some limiting value, some final value of a to the n with binomial coefficients. But these binomial coefficients can be rewritten as 1 plus na plus n times n minus 1 over 2 times a squared. And then the next one, n times n minus 1 times n minus 2 all over 3 factorial times a cubed. And then, in fact, there's no need for us to restrict to integer positive integer values of n. If n is a positive integer, like 5, then this series will eventually stop, because you'll eventually get to n minus 5. But if n is not a positive integer, this gives an infinite series. Particularly important is this one, the series for 1 plus a to the half, well, which starts off as 1 plus a half a plus a half times minus a half over 2 a squared, and so on, and it just keeps on going. So binomial theorem, that binomial series, that was one of Newton's favorite tools, and he used it to investigate the circular functions. Sine and cosine, of course going back to antiquity, but he analyzed them algebraically in this sort of power series point of view. And how he did it was rather interesting. He started with something which is essentially it's something like this. So the arc sine, if you define this to be the integral of square root of 1 minus t squared dt. Okay. So what you can do then is you can think of this as being a special case of this more general thing here. So you can rewrite this as 0x 1 minus t squared to the minus a half dt. And then you can apply this kind of binomial series to 1 minus t squared to the minus a half and expand that out as a series. Once you've expanded it out as a series, you can integrate it term by term. So Newton, integration meant you expand it out as a series and then you integrate term by term because you know what the integral of x to the n is. That's all what you need to know. He didn't think in terms of various rules for integration. There was only one rule for integration. That was the integral of x to the n is what it is, x to the n plus 1 over n plus 1. So his strategy would always be to evaluate everything as a power series first and then integrate, and the integration is relatively trivial. So what you get when you do this is this series, x plus 1/2 x cubed over 3 plus 1 times 3 over 2 times 4 x to the 5 over 5 plus 1 times 3 times 5 over 2 times 4 times 6 x to the 7 over 7 and so on. Now that's a much less well-known formula than the formula for the power series of sine of x. I suspect many of you will know the formula for sine of x, but perhaps this one, maybe you'll have seen it, but you probably can't remember it. I'm like that too. But it's rather remarkable that Newton discovered this one first and then used it to find the value, the power series for sine x. Okay, he didn't know what the power series for sine x was. He found it by a lot of work after he got this one. So basically he said, all right, suppose that y is equal to sine inverse of x, which is just that thing there. Then, okay, then sine of y is equal to x. So how do we write sine of y? Well, we have to invert. We have to take y equals this formula, x plus 1/2 x cubed over 3, etc., blah, blah, blah. We're calling that y. And now we have to solve for x in terms of y. How do you solve for x in terms of y? Well, you have to let x be a power series in y with undetermined coefficients, just like we did before. You have to plug in. Each one of these is going to become a series. You have to do a lot of algebra. Eventually, you find out that sine of y is, what is it? It's y minus y cubed over 3 factorial plus y to the 5th over 5 factorial minus y to the 7th over 7 factorial and so on. And you can imagine his excitement when the smoke clears, all the algebra somehow becomes dramatically simple, and instead of getting something incredibly complicated, you get this pretty pleasant formula. Okay. But it turns out that Newton was not the first to have discovered that formula. Okay. It turns out that these formulas for arc sine, they actually go back to Indian mathematicians. In Kerala, in the southern province of India. Kerala, I think, yeah. At least 100 years, maybe a couple hundred years before Newton. Not way long back, but a couple hundred years before Newton. They were very interested in astronomy, and they had very sophisticated mathematics. Okay, so that was Newton, and now let's say a few words about Leibniz, who was a German mathematician who also shares credit with Newton in the discovery of the calculus. And unfortunately, there was quite a big bickering between Newton and, well, not between Newton and Leibniz, but then also between the followers of Newton and the followers of Leibniz. And it soured relations between the British mathematicians and continental mathematicians for quite a while. And in fact, it also set back the British mathematicians, to be honest, in a serious way. So Leibniz did not have the power of Newton, but he thought long and hard about notation. And it's remarkable that the notation that we use in calculus in the year 2011 is basically Leibniz's notation. Okay, so he introduced this sign for sum. Well, it was kind of an extended, it's a S, like a German S for sum as an integral. And he introduced this notion of dx as an infinitesimal. And his orientation to calculus was quite different from Newton's. So Leibniz was interested in closed forms. So we get from him and from his followers the familiar formulas for integration, integration by parts, by substitution, and the way Leibniz thought about this is in terms of sums and differences. So here is some function. He thought of adding up a lot of little intervals to form a big area. And he was thinking that this is some kind of analogous to a more discrete kind of summation difference calculus. So for example, suppose you have a series 1, 2, 3, 4, 5. That's just a series, or a sequence, perhaps we should say. Then what you can do is you can form the sums. 1, 3, add one, then add the next one, 6, 10, 15. This is a series of sums that you get by summing the original sequence. Okay. So that's sort of one operation. To go from the sequence to this sequence, you take sums. But he realized that if you wanted to go backwards, you take differences. Okay. To go backwards, you take differences. In other words, if you wanted to recover the 5, you just look at the 10 and the 15 and you take the difference between those and you get the 5 back. So taking differences of a sequence and sort of summing them up are kind of inverse operations. And that was his motivating idea for his version of calculus. He was thinking that what we're doing when we're integrating is we're summing all of these things up. Yeah? And when we're taking a d of something, d to him was really a symbol for difference. So for example, he would have said that if you have some function f of x, and then you take the integral of f of x dx. Okay, there's the integral of f of x dx. It's that area under there. If you take d of that area is a lot like the sum. The difference between the d of that means sort of the final value minus the previous final value. Okay, that difference would be that rectangular thing there. Now, if the x width here was some small amount dx, then if you divide this by dx, let's put it there, you divide this difference by dx, then you're just going to get the height of that rectangle, which is f of x. And here, this is his explanation of the fundamental theorem of calculus, that if you take a function and you integrate it, and then you differentiate that, you get back the original function. Now that's the fundamental theorem of calculus. That actually was already known to people earlier than Newton and Leibniz. It was known to Barrow and I think Gregory. Okay. So there were a lot of contributors to this story. But Leibniz, after establishing his notation, sort of his point of view, he was very good at promoting it and encouraging others to use his notation. In particular, he was very good at, he got the Bernoullis, famous Swiss family of mathematicians, to adopt his thinking. And it didn't take long before everybody on the continent was thinking about calculus using the Leibniz sort of point of view. And that was very powerful because his notation was so good. It's so good that we basically still use it today. It's really remarkable that the originator of this, we haven't really improved markedly on his notation. We've changed our meanings about what the words mean a little bit and how we introduce them, but the notation is still exactly the same pretty well. Okay, so the tools were set. We now come, it's kind of a golden age of mathematics that results from this fabulous tool. So next time we'll talk about infinite series and move on to Euler's contribution and others, some of the remarkable things that people discovered with this calculus. So see you then. Today we're going to talk about infinite series. And the main mathematicians in this section is, well, first of all, Newton and Gregory, whom we've already met, but some new people, some 18th century mathematicians. Well, first of all, the Bernoulli family. Okay, so this is the most significant family of mathematicians in the history of mathematics, the Bernoullis. Jacob, 1654 to 1705. Then there was John, 1667 to 1733. Nicholas, 1687 to 1755, maybe, I'm not sure. Daniel, 1700 and 1782. So I guess two of these were brothers. One was a nephew. Maybe three of them were brothers, something like this. And then we meet the giant of sort of the modern age, Leonard Euler, whose dates are 1707 to 1783. And we might mention also Joseph Lagrange, who was in some sense the heir to Euler, 1736 to 1813. And there were other figures as well. Okay, so we talked a little bit about infinite series last week when we were talking about calculus. So let me remind you what the basic setup is there. We're thinking about expressions like 1 over 1 minus x, which is 1 plus x plus x squared plus x cubed, and so on. This is, in fact, the most fundamental of all infinite series, since it's really a geometric series. And we saw that it was a favorite of Newton, and it can be used to derive a lot of other different series. Now, these days, we think about series. We study them in first-year calculus, and we think about series like this in terms of whether they converge or diverge for a particular value of x. This is not really the way the 18th century mathematicians or the 17th century mathematicians thought about infinite series. They rather thought about them as some kind of extended or infinite polynomial. So these are really infinite polynomials, and one really wants to do polynomial arithmetic with them. So, for example, to justify this expression here, they would have said, well, we can justify it by cross-multiplying 1 equals 1 minus x times 1 plus x squared plus x cubed, and so on. And if we just think of that as a product of polynomials, albeit infinite polynomials, then we can expand in the usual way and collect terms. So 1 times this whole series would be 1 plus x squared plus x cubed, and so on. And then minus x times that same series would be minus x plus x squared plus x cubed plus, and so on. And then if you look at the sort of the difference between these two infinite expressions, it's kind of obvious that everything past this first one gets canceled in the second series. And so, indeed, the product of this times this is in fact 1. And that's an algebraic calculation. It doesn't really have anything to do with convergence at all. So the notion of convergence of a sequence was floating around. They were still interested in things converging, but it really didn't come into focus till probably the 19th century, when Cauchy made more clear what exactly it meant for a sequence to converge. But during the 18th century, a kind of algebraic point of view was the dominant one. Okay, so we can manipulate this in a lot of ways. One very simple way is simply to replace x with minus x. And then we get 1 over 1 plus x equals 1 minus x plus x squared minus x cubed plus, and so on, in alternating plus and minus terms. Now, this gives rise to an interesting kind of conundrum, because if you set x equal to 1 in this series, then you get 1 half equals 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. And this was an early kind of conundrum that puzzled the 18th century mathematicians, how to deal with this kind of expression. Because they realized that you could also rearrange this quite easily. You could think of this also as 1 minus 1 plus 1 minus 1 plus 1 minus 1. And when you did it that way, you obviously got 0. But if you rearranged it a slightly different way, if you said, well, this is 1 minus, and then we'll group these two terms together, 1 minus 1. And then minus 1 minus 1 minus 1 minus 1. And so on. Then all these 1 minus 1s are 0, and then we get 1. So clearly something is a little bit fishy here if a half is equal to 0 is equal to 1. And so there was definitely a conundrum, and people debated what is the right way of thinking about infinite series like this. I'm not sure if it was entirely resolved, but I think one thing that sort of became clear as time went by is that there's a sort of a big difference between working with polynomials and x's and working with a series of numbers. Okay, so basically, algebra with infinite polynomials, or power series, is often safer than calculations with infinite series of numbers. Safer than infinite series of numbers. Well, I mentioned just a few things that we've already touched upon, but if we take this 1 over 1 plus x series and we integrate it, then we get log of 1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. So that's obtained from, let's call this star, from star by integrating. And another important series that was one of Newton's favorite was the binomial series for a general exponent p. 1 plus p times x plus p times p minus 1 over 2 times x squared plus p times p minus 1 times p minus 2 all over 1 times 2 times 3. Maybe we could write that as 1 times 2. X cubed, and so on. So this is finite. This is a finite sum if p is a positive integer like 5, because of these terms here. If p is 5, then eventually they all become 0. But otherwise, it's infinite. Now, there's an important formula that I want to talk about because it's rarely mentioned in calculus books these days, although it's both historically very important and it's also, I think, quite of independent interest. So this is a formula that ought to be in calculus text, but often isn't. It's the Gregory-Newton interpolation formula. And it arises when we have a function which is known at a regular sequence of points, whose values we know at a regular sequence of points. So for example, suppose we have a point A, and then over somewhere A plus B, and then over a little bit further, A plus 2B, A plus 3B, and so on. So we have a separation of B between all these adjacent points. And the question is, if we know a function f at all these equally spaced points, can we recover the function's values at intermediate points? That's the question. If f of x is known for all these points x equals a plus nb, where n is 0, 1, 2, and so on, then what is f of some random point? Is there any way of figuring out or interpolating using the information from these discrete points to figuring out what the function should be in between? And it turns out that for many functions at least, the answer is yes. In particular for polynomials and for power series functions, the answer is yes, and the formula is a very interesting one. Okay, what is it? Well, to introduce that, I need to talk a little bit about a difference operator. It's natural whenever you have a sequence, you can take differences of successive elements in the sequence, and you get another sequence. And the standard notation for the difference operator is this little triangle operator. So we define delta f at some point, let's say a, to be f of a plus b minus f of a. So the value at B more minus the value at A. So we can do that at not just at A, but we can do it also at A plus B. So that would be f of A plus 2B minus f of A plus B, etc. And then you could take the difference of the difference, usually denoted with a delta squared, f of A. So that's the difference operator f at A plus B minus the difference delta f at A. So if you take this formula and you subtract this one here, then explicitly you're going to have f of A plus 2B minus 2f of A plus B plus f of A. And then you can take the third difference. Well, that would be the difference of the second difference of f of A plus B minus the second difference of f at A. And that turns out to be f of A plus 3B minus 3f of A plus 2B plus 3f of A plus B minus f of A. And so now in terms of this notation, this difference operator notation, here is the interpolation formula of Gregory and Newton. That f of A plus h, where h is now some rather random step, not necessarily a multiple of b. This is f of A plus h over b times the difference del f of A plus h over b times h over b minus 1 all over 2 factorial times del squared f of A plus, and so on, and I'll write the next one, h over b times h over b minus 1 times h over b minus 2 all over 3 factorial times del cubed f of A, and so on. So what is needed here in order to compute is we need to know the function's value at A. In order to calculate this thing, we only need to know its value at A and at A plus B. To know this thing, we need to know its value at A plus B, and A plus 2B, and so on. So all what we need for the entire series is just to know the function's values at these discretely spaced points. And then, if we know that, we can cook up this expression that allows us to calculate, say, a value there. That would be h. So that's f of A plus h. That would be that point there. We would be able to calculate the function's value at that intermediate point. Now, a little bit of thought shows this is not going to work for an arbitrary function. If you just draw some random function, there's no way that the function can tell what the intermediate values are from the values just at these points. But it does work for polynomials. Works for polynomials f of x. And more importantly, it works for power series functions, which are the kinds of functions that Newton and contemporaries were really interested in. And power series functions. Now it has an interesting consequence also, that if you look at that formula and say, what happens if this separation starts becoming very small? If B starts getting close to 0, then these equally spaced points become closer and finer, approaching sort of a uniform grid. And then the formula sort of simplifies into something more familiar involving derivatives. The formula due to Brooke-Taylor, called the Taylor series of the function. So as b approaches 0, we get Taylor's theorem. And Taylor was also a contemporary of Gregory and Newton, but maybe 40 or 50 years afterwards. So what's the idea there? Well, the idea is that, well, I'll write down what Taylor's theorem is. It's that f of a plus h equals f of a plus, I'll write the h on this side, although it's usually more common to write it on the other side, h times f prime of a plus h squared over 2 factorial times f double prime at a plus h cubed over 3 factorial f triple prime at a, and so on. And the reason is that when you look at an expression like this, say if you look at this thing here, that coefficient del f of a over b, what was del f of a? It was actually f of a plus b minus f of a. So if we divide that difference by b and let b go to 0, that's exactly the derivative of the function at a. And similarly, the next term, for example, if you look at del squared of f at a divided by b squared, then that goes to the second derivative at a. So for example, in the second thing here, if you take this factor of b out and put it in front under there, then it'll be essentially an h squared left up here. And then this divided by the b squared goes to the second derivative. One of the reasons these days that this interpolation formula is maybe not considered important enough to make it into a lot of calculus texts is that these days we have calculators to compute a lot of standard functions for us. But in the 17th century, people had tables to compute things. And the tables were constructed with a lot of work. So Napier constructed tables of logarithms, for example. So if you wanted to know what the log of 4.3974 was, whatever I said, okay, you wanted to know what that thing is, then you had to look in the logarithm tables, and maybe you could find a value for log of 4.7. You knew what that was, and maybe you knew what log of 4.8 was. But that was as much information as the tables gave you. So you had to either eyeball, well, say we're somewhere in between here, closer to here, right? And you could kind of guess. But they wanted to do better than that, so they wanted to have a more systematic way of how do you go from a table of known values to calculating a value somewhere in between. Very practical, important problem. And so you could see the motivation for the interpolation formula. Interpolation was a big deal back in those days. Okay, so now we come to Leonhard Euler, who was, as I've said repeatedly, the most important and greatest mathematician of the modern era, and second only to Archimedes in terms of the greatest mathematician of all time. He was a remarkable person who was born in Basel in Switzerland and spent a lot of time at the Academy in Berlin. And he also bounced back and forth to St. Petersburg in Russia, where he ended up spending most of his career. And he had a long and prolific career. He also had lots of children. He was very pious, religious, sort of plain-spoken person. And he produced huge amounts of first-rate mathematics. So he produced more mathematics than anybody else in history, much more than anybody else, really. His collected volumes, would extend beyond the reach of my arms. During his time in Berlin and St. Petersburg, there were academies where all the mathematicians were supported by an academy. Perhaps more than universities, it was these academies that sponsored academic research. And the academies would have a journal that would report and allow members to publish. And during his years there, he would often be responsible for 50% of all the publications of the entire academy in that year. Almost every week there would be a new paper by Euler. But they weren't just going over the same old thing, right? They were wide-ranging over all areas of mathematics. Everywhere he was interested, he had made contributions in every direction. So he's, in some sense, he's the father of graph theory. In some sense, he's the father of topology. He's probably the father of analytic number theory. He's a key figure in differential equations and the calculus of variations. Made important contributions to astronomy, to mechanics, to physics, to elastic bodies. Number theory, very important contributions to number theory. The list goes on and on. He pretty well did everything. And he also wrote very important textbooks. One of his textbooks, which is called the Introductio in Analysis Infinitorium, something like that. Introductio in Analysis Infinitorium, published in 1748. It's really the world's first calculus textbook. And some people have said it's also the world's best calculus textbook still. That I've heard people argue that students at universities in 2011 would be much better off if they ditched their first-year calculus books and all studied from Euler's work 250 years ago. There's probably something to be said about that. So almost so many things so standard topics that you learn about were first treated by Euler and laid out very clearly by Euler in works like this. So let me just very selectively choose a very few things. Okay, one could talk for weeks about what Euler did, but I'll just mention a few small things to give you a sense of some of the things that he was doing involved with infinite series. So the first kind of series that people tried to calculate, which they couldn't, was this one. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. The sum of the reciprocals of all the squares. Now, people knew for a long time that the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, etc., okay, that actually diverges. That goes back to Oresme in the 1300s, maybe 1350. Oresme realized that this series diverged, which means that if you keep adding those terms, even though you're adding less and less all the time, the total grows slowly and slowly and slowly beyond any bounds. Never stops, just keeps on growing bigger and bigger and bigger. And the way Oresme realized this was to say, look, here's the argument. We're just going to think in terms of grouping these terms in powers of 2. So we'll group this one together, and then we'll group these two together. And then we'll group the next 4 together, and then the next 8, and so on. And by doing that, he could observe that this group of 2 here, 1/3 plus 1/4, that's bigger than 1/4 plus 1/4. Okay, that's bigger than or equal to 1/4 plus 1/4, which is 1/2. And this next group of 4 terms is bigger than what you get when you replace each of one by the smallest. 1/8 plus 1/8 plus 1/8 plus 1/8. And 4 times 1/8 is also 1/2. And then if you take the next 8 terms and you add them up, you compare them all to the last term, which is 1/16, you get another group which is bigger than 1/2. So you can keep taking a segment of the series which is bigger than 1/2, and you can keep doing that as far as you want. So it's 1/2 plus 1/2 plus 1/2. It goes up beyond any limit. So we say it diverges. But it was pretty obvious that this thing didn't diverge, that it actually zeroed in on some number. If you keep adding these things together, it doesn't keep getting bigger and bigger and bigger. It starts approaching something because the numbers that you're adding are in some sense smaller than the numbers over there because you're squaring them. The Bernoullis made lots of calculations with various series, and they knew how to calculate various series, but it was Euler who first established this thing, and sort of remarkable thing. It's pi squared over 6. Which made people stand up and pay attention because pi, what's pi doing in there? Pi squared over 6. Well, we've seen that pi, we have expressions for pi in terms of 1 and 1 minus 1/3 and so on. So it's maybe not that surprising, but it was still a fabulous formula. And it's interesting to see how Euler got it. Okay. He derived some interesting things along the way. So he used Descartes' factor theorem. This was a result, very important result of Descartes, which people learn in high school, which is that if P is a polynomial and P of, say, some value R equals 0, then X minus R is a factor of P of X. So zeros of polynomials correspond to factors of that polynomial. So back in those days, these mathematicians all knew about each other's work largely. Euler would have known all of Descartes' work and Newton's work. He would have studied their works. There weren't that as many mathematicians as there are now. And so it was a little bit easier to keep track of things. And they would write letters to each other. There would be a lot of correspondence. Euler corresponded a lot with the Bernoullis and with other people. So what's the proof of this, of Descartes' thing? Well, suppose that the polynomial, let's write it as P of X equals A0 plus A1X plus A2X squared. Let's go up to AN X to the N. And let's just substitute another value, say y, right below it. A0 plus A1y plus A2y squared, and so on. ANY to the N. So if you take the difference between these things, you get P of X minus P of Y equals, well, these cancel, and you'll get A1 times X minus Y plus A2 times X squared minus Y squared, and so on up to A sub n times X to the N minus Y to the N. But each one of these terms is divisible by X minus Y. We all know that X squared minus Y squared is X minus Y times X plus Y. But that's also true for these higher things. So if you take something like x to the n minus y to the n, you can write it as x minus y times x to the n minus 1 plus x to the n minus 2 times y plus x to the n minus 3 times y squared, so decreasing powers of x, increasing powers of y, all the way up to eventually just y to the n minus 1. That's like, for example, x cubed minus y cubed is x minus y times x squared plus xy plus y squared. And since that works for all of those factors, we can write this as x minus y times some polynomial q of x. Because we can take that factor of x minus y out from all of the terms on the right-hand side. So that's a general relation. And now suppose, let y be r, where r is our 0 of the polynomial, where p of r equals 0. What are you going to get? Well, on the left-hand side, you're going to get p of x minus p of r, but p of r is 0, so you'll just have p of x. And then on the right-hand side, you'll have x minus r times q of x. So if r is a 0, in other words, if p of r here is 0, then p of x is x minus r times some polynomial. So that's a proof of Descartes' factor theorem. Okay, so how did Euler use Descartes' factor theorem to derive this remarkable identity with the sums of the reciprocals of the squares? Well, what he did is he applied it in a rather ingenious, maybe somewhat courageous way. He applied it to something that you might not think about applying the factor theorem to, something which is not exactly a polynomial, namely to the function sine x. Okay. Euler knew that it was pleasant to think about sine x as a function, and that you could graph it in the usual way. Okay, and it goes from the values 1 to minus 1, and it has 0 at 0, and it has a 0 at pi, and at 2 pi, and at 3 pi, and also at minus pi, and at minus 2 pi, and so on. So sine x has zeros at, well, at x equals 0, at plus or minus pi, and plus or minus 2 pi, and so on. So Euler said, okay, why don't we think about that as a polynomial? I know it's not a polynomial, but let's imagine it's a polynomial. What kind of polynomial has zeros at x equals 0, plus or minus pi, plus or minus 2 pi, etc.? Well, you have to think a little bit about whether those zeros are single zeros or double zeros or triple zeros. But you can kind of tell the way the graph goes through each of these that these are just single zeros. They're not zeros of this kind, like y equals x squared kind of zeros. Meaning that each one of these corresponding factors should really appear exactly once in the factorization of sine of x. Now, most students will not have seen the factorization of sine of x, but Euler wrote it down. So what is the factorization of sine x? Well, here it is. Sine x is, well, it has x as a factor because it has a 0 at x. But it also has factors at plus or minus pi. And for each one of those, there's a factor like this. This is actually combining the factor at pi and at minus pi. Okay, it's a little bit, it doesn't look quite like a usual factor, but instead of writing pi minus x, so instead of writing pi minus x times pi plus x, I'm taking this thing here and dividing both of them by pi squared. We could always normalize. So if we divide by pi squared, then that means that coefficient is 1. That's kind of good. And then there's a corresponding term for the next pair, the 2 pi and the minus 2 pi. 1 minus x squared over 2 squared pi squared. And then 1 for the next pair, 1 minus x squared over 3 squared pi squared, and so on. So this is an infinite product, not an infinite sum. It's like a polynomial with a lot of factors, infinite number of factors. Now, Euler had to know something to do this. Well, he had to know quite a few things, but he had to know. Yeah, you need to know that if you look at sine x over x, that ratio goes to 1 as x goes to 0. So if we divided this by x and let x go to 0, then each of these terms would come close to 0, and then the whole thing would go to 1, which is telling us that there's no constant here. There's no constant like phi or pi or anything else out front. The constant is actually 1 as a result of that. Okay, so now what did Euler say? All right, now Euler said, well, let's just expand this thing out. So expand. How do you expand it out? Well, it's just like a polynomial. The lowest power is x. You get x by multiplying 1 times 1 times 1 times 1, keeping on going. So that's the first term, x. What's the next smallest power of x? Well, it'll always be this x. So the next thing you can multiply it by is an x squared. So there'll be a minus x cubed. And what's the coefficient of minus x cubed? How do you get an x cubed? Well, you get it by taking this times this and all the other ones, or this times this and all the other ones, or this times this and all the other ones, and so on. So the coefficient is, here it will be 1 over pi squared, and here 1 over 2 squared pi squared, and over here 1 over 3 squared pi squared, and so on. And then there's additional terms. The next one would be x to the 5th times something. You can try to figure out what that term might look like. But Euler knew also, as did Newton, that sine had also the expression x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So that goes back to Newton, or indeed to the ancient Indians. Okay, but now we're in a position of comparing. Now we can compare this term with this term here. They've got to be equal. So you compare coefficients of x cubed. And what do you get? Well, you get that 1 over pi squared times 1 plus 1 over 2 squared plus 1 over 3 squared plus, and so on, equals (1 over 3 factorial). And so if we multiply by pi squared, we get the sum of this series is pi squared over 6. He also established that 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus 1 over 4 to the 4th, and so on, that had a similar expression. In fact, maybe you can try to derive that from this by looking at the next terms. That's equal to pi to the 4th over 90. So try it. In fact, he got a formula for all the even powers. So in general, 1 over 1 to the 2n plus 1 over 2 to the 2n plus 1 over 3 to the 2n plus and so on. He got this formula. That's minus 1 to the n minus 1 times 2 pi to the 2n over 2 times 2n factorial times b sub 2n. Okay, what is b sub 2n? It's a Bernoulli number. B sub 2n is a Bernoulli number. Okay, these were introduced by James Bernoulli in some work on probability. And I'll tell you what some of the values are. So b sub 2 is 1/6. B sub 4 equals minus 1/30th. B sub 6 equals 1/42nd. B sub 8 equals minus 1/30th. B sub 10 equals 5 over 66, and so on. And probably the easiest way of defining what they are is through this power series. That if you take x over e to the x minus 1, what is that? Well, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. So if you subtract 1, you just remove that and there's an x on top. So if we divide sort of by x, this is the same as 1 over 1 plus x over 2 factorial plus x squared over 3 factorial plus and so on. So if you take the inverse or the reciprocal of that infinite series, then you will get the sum n equals 0 to infinity, b sub n x to the n over n factorial. That's a definition of one definition of the Bernoulli numbers. Again, this is something you can do by hand. You could just take the reciprocal of this or try to find the reciprocal of this by letting it be as some arbitrary sequence and multiplying this by that arbitrary series and equating coefficients term by term. Bernoulli also gave a recursive definition for the Bernoulli numbers in terms of previous Bernoulli numbers, but we won't write that down. So one thing that's kind of interesting here that maybe we should remark on is that this formula for the sum of the reciprocals of the powers, well, we have one for the sum of the reciprocals of the squares. We have one for the sum of the reciprocals of the 4th powers and also of the 6th powers and the 8th powers and so on. But we don't have any formula for the sum of the reciprocals of the 3rd powers or the 5th powers or the 7th powers. In fact, no one knows a formula for those ones. It's a famous unsolved problem. No one knows a formula for the sum of the reciprocals of the cubes. In fact, only in 1981, I think, did a French engineer, I think it was, I don't think he was a professional mathematician, named Apéry, discover a nice elementary proof of the fact that case 3 is actually not a rational number. So to talk a little bit more sensibly about that, Euler talked about the zeta function. So we can introduce a function. We can define zeta of s, say, to be 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s, and so on. So what do we know about this? Well, we know that when you let s equal 1, then you get infinity because the harmonic series blows up. That's our res-based result. Okay, that means it has a pole. And we know that zeta of 2 is pi squared over 6. And we know that zeta of 4 is pi squared over 90, pi to the fourth over 90. And it was only in 1981 that A. Paris proved that zeta of 3, whatever it is not a rational number. I remember when that happened. That was quite a remarkable thing, because no one thought that you could kind of get at that through elementary means. So we don't know what the story is for the other odd values, and we don't really have an expression for a zeta of 3. This is sort of typical what happens if you write down some random series. These aren't random series, but if you write down a random series and ask, well, what's the sum? It's almost never the case that you can be able to say what the sum is, except to say that it's just itself. It's just the way it is. So I can't leave the zeta function without mentioning a very important factorization that Euler discovered for the zeta function, which turned out to have very big ramifications for mathematics in the 19th and 20th century. This is the this formula here that you can write it as an infinite product. Euler liked infinite products, just like sums. And here's the product. 1 over 1 minus 1 over 2 to the s times 1 over 1 minus 1 over 3 to the s times 1 over 1 minus 1 over 5 to the s times 1 over 1 minus 1 over 7 to the s. What do you think the next term is? 11, yes. 1 minus 1 over 11 to the s. So it's a product over all the prime numbers. Okay, all the prime numbers here. And, well, each one of these is like an infinite geometric series. So this first one here is really the infinite geometric series 1 plus 1 over 2 to the s plus 1 over 4 to the s plus 1 over 8 to the s, and so on. And then the next one is all powers of 3. 1 plus 1 over 3 to the s plus 1 over 9 to the s, and so on. The next one's all powers of 5. 1 plus 1 over 5 to the s plus 1 over 25 to the s, and so on. And once you write it this way, it's almost becoming clear why it's true. Okay? The reason it's true is because of the unique factorization of numbers. We know that every number factors into primes in exactly one way. So for example, if you look at 12, okay, 12 is 2 times 3. So if you look at the term 1 over 12 to the s, just look at where does that come from? Well, that comes in this product by taking the term 1 over 4 to the s and multiplying it by 1 to the 3, 1 over 3 to the s, and using the 1s for all the other factors. And since you can kind of do that for every natural number, you can factor it, and then you can sort of see which, how many powers of 2 do you need, how many powers of 3 do you need, how many powers of 5 do you need, and so on, to express that number. That will correspond to the factorization. This function of s, zeta of s, it blows up at s equals 1. What does it look like? So there's s equals 1. It blows up. At s equals 2, here's s. At s equals 2, we know it's pi squared over 6, which is, I don't know, a little bit somewhere between 1 and 2. And then at 3, it's something will be, so it goes down like this, some way, and blows up. it doesn't look that interesting, but it turns out that you can extend this zeta function to complex values. Once you know about complex numbers, you can define what this zeta function means for S being a complex number. Okay, well, yeah, so if you have the complex plane with 1 here and I here, then this function, which we've just been talking about so far, having values on the positive real line, can be extended into the whole complex plane. And then it turns out that, okay, it's got some zeros here somewhere, but there's this line, the line where the real part is a half. Okay, and it turns out that Riemann, great German mathematician of the middle of the 19th century, conjectured that this extended zeta function, once you'd extended it to the complex numbers, that all of its non-trivial zeros lie on this line, real part equals 1/2. And that's the most famous problem in mathematics today. That's the most famous problem. It's called the Riemann hypothesis. And you might say, well, why should that be famous? Well, it's because it tells a lot about prime numbers. So all kinds of deep properties of the prime numbers are encoded in this analytic information about where the zeros of this zeta function are. And the fact that it has something to do with prime numbers is already obvious from Euler's product expansion. Okay, but it does take some significant analysis, complex analysis too, and some number theory to appreciate the Riemann hypothesis, its full glory. But there's a lot of evidence for it. So Euler established a lot of the foundational work on sort of high school and undergraduate mathematics that we deal with today. And in particular, he understood the exponential and logarithm functions very well, and they were very important to him. And he also investigated those functions in the complex plane. So in the 18th century, people started working with complex numbers a little bit more confidently than they did in the 17th century. And Euler was quite adept with complex numbers, as we'll see. So I remind you that if x equals log y, then y is the inverse function, which we call e to the x. And perhaps the best way of introducing these functions is to start with log y. So log of y is defined to be the integral from 1 to y of 1 over t dt. This is a definition of log. And then it's not too hard to see that the derivative of the log function, because it's an integral, so its derivative is just what's inside here, so it's just 1 over y. So in other words, dx dy equals 1 over y. Then if we invert that, then it means that dy dx equals y. Just flip it over. And y being e to the x, it means that this function y has the property that its derivative is equal to itself. So the inverse function of the log function has the very special property that its derivative is equal to itself. And from the power series point of view, it means that you can write it down as a power series, and you can sort of figure out what it is step by step, because it's got to be equal to its derivative. We also know its value at 0 is 1, so if it starts with 1, then the next term has to be x, because the derivative of this has to be that. And then the next term has to be x squared over 2, because the derivative of this has to be that. And then the next term has to be x cubed over 3 factorial, because the derivative of this has got to be that. So you get the power series for the exponential function. By the way, Euler liked to write it as 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3, and so on. Euler liked to be very explicit about things. He wrote things out fully, and he was not afraid of making calculations and having a long formula. In terms of pictures, if we have x and y, if we start with the function 1 over x, and there's 1, and we integrate it to get the log function, then we get log of x. So this is just the area underneath the 1 over x function. And if we look at the various values, 1, 2, 3, 4, 5, and so on, then the area underneath that curve can be approximated with a bunch of rectangles. The first rectangle will have height 1, and then the next rectangle will have height 1/2, because that's a half, and then the next rectangle will have height 1/3, and so on. And so in some sense, there's an approximate sense in which the log function should be a lot like the first few terms of the harmonic series, so that 1 plus 1/2 plus 1/3 plus all the way up to, say, 1 over n should be pretty close to log n. The integral is approximated by all those areas of rectangles. In fact, Euler realized that the difference between those two things approached a certain number. The limit as n approaches infinity of 1 plus 1/2 plus 1/3 plus all the way up to 1 over n. If you subtract log of n, you get some number, usually called gamma these days, has the value, approximate value, 0.57718 ... And that's known as Euler's constant. Euler also used the exponential function with complex values, and he came up with the famous formula e to the I theta equals cos theta plus I sine theta. Familiar to all students of complex numbers, complex analysis. I want to read a little bit from this Introductio in Analysis Infinitorium. It's a section on circular functions. So the circular functions, cosine, sine, tan, and so on, they're quite a source of logical problems in undergraduate mathematics, because it's rare that you actually pin them down very precisely. Most treatments of calculus sort of suppose that these functions have already been defined back in high school, and that's not necessary to be very clear about what these functions actually are and what the various proofs of the various claims made about them are. So it's today a source of logical problems in mathematics. But anyway, here's Euler talking about, in his rather introductory text, about how we should go about thinking about these functions. So after logarithms and exponential quantities, we shall investigate circular arcs and their sines and cosines, not only because they constitute another type of transcendental quantity, but also because they can be obtained from these very logarithms and exponentials when imaginary quantities are involved. Let us therefore take the radius of the circle to be 1. Then it is obvious that the circumference of this circle cannot be expressed in rational numbers, but it has been found that the semicircumference is, by approximation, pi equals 3.141592653589793, and Euler then goes on for 127 decimal places. So there's someone who's serious about calculus. Okay? Doesn't say that it's just roughly 3.1414. It's 127 decimal places. He gives it to you. Okay. For which number I would write for short pi. So that pi is the semicircumference of the circle of which the radius is 1. Or pi is the length of the arc of 180 degrees. Now, if we denote by z an arbitrary arc of this circle, then we shall usually consider of this arc mainly the sine and cosine. I shall denote the sine of the arc in the future in this way by sine of z. Maybe that's z there. Sine of z, and the cosine by cosine z. And he mentions that sine of 0 is 0, cosine of 0 is 1, and sine of a half of pi over 2 is 1, and cosine of pi over 2 equals 0. And then he derives a whole host of other trigonometric formulas and identities which are well known. Then he says that since sine of z squared plus cosine of z squared equals 1, we shall have by factorization this formula, cosine z plus I sine z times cosine z minus I sine z equals 1. Here he's kind of making reference to what we would now say as, well, we have a complex number on the unit circle. Maybe W equals cos theta plus I sine theta. This is the statement that the complex number W times its conjugate is 1, which is equivalent to saying that its mod squared is 1. And then he mentions de Moivre's theorem, which is cosine n theta plus I sine n theta equals cosine theta plus I sine theta to the n. And from this he gets cosine of nz, okay, he's using z, cosine nz equals cosine z plus I sine z n plus cosine z minus I sine n z to the n over 2, over 2, plus a similar formula for sine z, sine nz. And then he says, well, now what we can do is we can expand these things out in terms of the binomial theorem. Because we have something plus something else to the nth power, we can expand that out. So when we develop these polynomials in a series, we shall get cosine nz equals cosine z to the n minus n times n minus 1 over 1 times 2 times cosine z to the n minus 2 times sine z squared plus etc. And similarly a formula for sine nz. Now he says, now let the arc z be infinitely small. So let z be very close to 0. Then we get that sine of z is equal to z. So if z is very small, sine of z and z are almost the same. And cosine z equals 1. Now let n be an infinitely large number. Okay? Now let n be almost infinitely large. So this is going to get infinitely small. This is going to get infinitely large. But their product should be something that we understand. But such that n times z equals a finite value v. Okay, so this is the kind of argument that these days we might be a little bit skeptical about, or we would maybe want to say it in some more precise way. But typically, whatever Euler said, there was some more precise way of saying it, but this is the language he used. Okay, so what happens to a formula like this? Well, then this kind of simplifies. Then we get that cosine v equals, so cosine z we're saying is 1, okay, that's 1, and then minus n times n minus 1 over 1 times 2 times cosine z to the n minus 2, and he ends up getting v squared over 1 times 2 plus v to the fourth over 1 times 2 times 3 times 4, and so on. In other words, he gets the usual power series for the cosine function from this using some kind of limiting arguments. And I'll just say, give you a few more formulas that he writes in this chapter. So including the formula as he writes, 1 plus z over epsilon to the z epsilon equals e to the z. So this where epsilon is, okay, it's 1 over n as n goes to infinity. Oh, no, maybe I should say, no. Where epsilon is infinity, we would write e to the z equals limit as n approaches infinity of 1 plus z over n to the n. And then he writes down the famous formulas, cosine v equals e to the iv minus e to, plus e to the minus iv over 2. And same sign of v equals e to the iv minus e to the minus iv over 2I. Well, this only touches on a very small part of all of Euler's work, but it's quite clear that a lot of the ways we think about the exponential functions, the log functions, the circular functions were well known to Euler, and basically we follow his treatment in a lot of different ways. But one big difference is that these days when we talk about series, power series in the calculus course, the emphasis is generally on convergence of series, whether a certain series converges or not. To Euler and his contemporaries, that was not really that interesting, because you could kind of think of a series as being some kind of infinite polynomial independent of whether it converged or not. So it turned out in the 20th century that that point of view kind of came back, and there's now a branch of mathematics called formal power series, which justifies, to a certain extent, a lot of the manipulations that Euler and his contemporaries made. And it may be, I think, that the future will still see perhaps a return to the more algebraic orientation to series and analysis that Euler and after him Lagrange sort of pioneered. So next time we're going to talk about arguably the greatest development in modern science, not just mathematics, but which is the mechanics initiated by Isaac Newton. So really the start of physics in the 17th century. So we're going to talk about mechanics and really the resolution of probably the greatest problem in the scientific history, namely what's happening with the planets. They figured that out in the 17th century, and so we'll talk about that. So I'll see you then. All right, so welcome to our lecture 11 in this course on the history of mathematics. Today we're going to talk about the resolution of what's almost certainly the greatest problem in the history of science. So the general topic is mechanics, but we're going to focus on the mechanics of the solar system. And the greatest problem of science historically has been to explain what's going on with the night sky. How to explain what goes on in particular with the planets. Figuring out what goes on with the sun and the moon against this backdrop of stars which are rotating above us every night, that's not too hard to do. But figuring out what the various planets are doing is a very complicated undertaking that all ancient civilizations were interested in. And many ancient civilizations created astronomical observatories to try to predict and to explain what was going on. And this was really the great achievement of the 17th century, where finally this problem was more or less solved, and with it the framework of science was erected. So the 17th century is really a high point of the history of mathematics. We're talking about the 1600s, roughly that period, which in my view is the most important century in history. If I had to rank the various centuries in terms of importance, I would put this one as the first, and the second one would be the 18th century, and then the third one would be the 19th century, and then after that I would rank the 20th century. In terms of the importance of the mathematics that was discovered in those various times. And nothing that we have done in the last 100 years in mathematics, at least, can really compare with the work of these gentlemen in resolving this most important problem. So let's go back to one of the people who really started it was Nicholas Copernicus, okay, a Polish astronomer who rather courageously tackled the dogma at the time, which was that everything goes around the Earth. So from Ptolemy, ancient Greek mathematician, 200 years after Christ, who was sort of the father of the subject in terms of having created this major work, the Almagest, that was sort of the Bible to later astronomers. So in his theory, there were epicycles, and it was Earth-centered. So we had the Earth, and everything went around the Earth in various ways. The sun went around the Earth, the moon went around the Earth, the various planets went around the Earth, Mars. The known planets at this time would have been Mercury, Venus, Mars, Jupiter, and Saturn. Aside from the Earth, those are the 5 planets that were known since ancient times. And although the moon and the sun's motions are reasonably predictable once you've studied it for a few years, the planets like Mars and Venus and Jupiter and Saturn are much more irregular. They kind of move around and they wander back and forth and they do strange things. So this was the framework that had been around for a long time, and this was what Copernicus challenged in his great work, which was only published near the time of his death. Okay. And in it he proposed that we should think about changing from an Earth-centered story to a sun-centered story. So it was a heliocentric system where the sun was at the center and everything more or less revolved around the sun. Well, actually, Copernicus was not the first person to have suggested that. That idea, in fact, goes back to the ancient Greeks also. So a notable Greek astronomer, I think it was Aristarchus, also suggested this. But it wasn't really taken, it didn't catch on, although Archimedes had a fair amount of respect for that. Ancient Greeks. In particular, when Archimedes, one of Archimedes' books is called The Sand Reckoner, and in it he proposes to calculate how much sand can fill up the universe. So it's an exercise in big numbers. And one thing that Archimedes realized, that if this idea was right, that the Earth actually went around the sun, then the other stars had better be very far away from the Earth. Because if the Earth is actually moving, goes around once a year, then the Earth is probably going a long distance from one side of the sun to the other. And that would mean that if you had some stars which were reasonably close, then they would look different from this position than from this position. So you would expect the configuration of stars to look different if this was the case, unless the stars were very, very far away. It's kind of a necessary consequence of having a heliocentric point of view, that the stars have to be very far away so that there's no parallax. Okay, so and Archimedes sort of realized this, incorporated this idea that the stars had better be very far away if we're actually going around the sun. Okay, so that's what Copernicus suggested, and he worked it out all out mathematically using essentially Ptolemy's mathematical framework. So trigonometry played a big role, spherical trigonometry especially, tables of chords that Ptolemy had used were all employed by Copernicus to try to give a mathematical model that sort of proved that this view fit with the data that had been collected at the time. And Copernicus ended up using a kind of epicycle approach of Ptolemy, that the orbits were more or less circles. Okay. The orbits were pretty well circular, or maybe we had to do circular plus some additional circular motion around the circles. Plus sort of other smaller circular motion. So Copernicus didn't get a lot of fame for this theory during his time because he died very shortly after it was published. But it did have a big influence on the subsequent mathematicians and astronomers. Let's talk a little bit about Galileo, famous Italian scientist, mathematician, astronomer also, who was, some people say, the father of science. Okay? Sometimes called the father of science, because he advocated a point of view to the natural world that said that it's really mathematics which is underpinning the scientific world that we're observing. That we should explain or try to explain the natural world by looking for mathematical laws. And he advocated sort of an empirical approach to things. He said we should actually go out and observe things. We should go out and observe things, make observations, make recordings, and see how they fit with our mathematical models and adjust things if necessary. Right? So it's sort of a foundational idea that you can get truth by going out and looking and being very careful, observing very carefully, then coming back and making your observations fit with some model. Okay? It's not self-evident that that approach works to explain the world. And it hadn't really been developed until his time. So father of science plus an empirical approach. Namely, observation was important for him. And one of the kinds of things that he was interested in is what happens if you drop a weight off a building. What do falling objects actually do when they fall? So here's a building, and you drop some object, and it starts to fall, and eventually hits the ground. And Galileo realized that this object sped up as it fell. That when it gets to the bottom, it's going faster than it was in the middle or up at the top. Okay, so falling objects speed up. Okay, that's good. But how exactly do they speed up? How do we describe this dependence of the velocity to where the thing is? Well, so he was thinking about a velocity, what's called the velocity v. Okay? And the velocity v probably depends on the distance that the object has fallen since it started. And it also probably depends on the time. So these various variables around, the time, the distance, the velocity. And at first, Galileo was unsure whether the velocity was proportional to the distance or whether it was proportional to the time. So these are two hypotheses. So one hypothesis is that the velocity is proportional to the distance. Whoops. So that you double the distance, the velocity is going to double too. Or velocity is proportional to the time. You double the time, and then the velocity doubles. And this was, both of them roughly correspond to our intuition. It's a question of going out and observing, as Galileo realized. It's the scientific approach. Armchair theorizing is only so good. We're talking about the physical world. We have to go out and actually look. And he went out and did experiments and made measurements and so on, and eventually realized that it's velocity that's proportional to time and not to distance. So in other words, the velocity ends up being some constant times the time. And that means that if you differentiate that, it means the acceleration, which is just the derivative or the rate of change of the velocity with respect to time, the acceleration is going to be constant. So he deduced that a falling object is experiencing a constant acceleration. It was a very key aspect to the way things move. So falling objects experience constant acceleration. And because he was interested in the motions of things, he was also interested in projectiles, which was a big thing at those days because people were perfecting their cannons. Right? And people were quite interested in, you wanted to bombard a city. How do you get your cannon? How do you slant it in the right way? So this sort of story of projectile motion. You've got a cannon and shoots off. And then Galileo realized that the arc of that projectile was essentially parabolic. Okay? Parabolic arc. So the 1600s, the 1700s, they were kind of a period of really vital, dynamic period in the history of science and math. There wasn't really such clear divisions in the various disciplines as we have now. Physics really hadn't been developed, or was really only developing at this time. There wasn't really a theory of chemistry. There wasn't really much of a theory of biology. Now we have a lot of compartmentalized disciplines. But back then, mathematics embraced astronomy. It embraced projectiles. It embraced optics. Sometimes it embraced astrology as well. But it would also embrace other things like maybe stone cutting or design, or architectural design. So the mathematicians of the day did not really think of themselves as just mathematicians. They thought of themselves as being interested in the world at large and just trying to explain what was going on. There weren't such clear boundaries as there are today. So almost all these major figures would have had a great interest in astronomical questions. That was always a really interesting subject. Galileo, we should also say, adopted Copernicus's heliocentric point of view. And at some point, the church, the Roman Catholic Church, started realizing that this was maybe not such a good thing according to the doctrine, because certain parts of the Bible refer to the earth as being stationary, and secondly, because it kind of makes us feel good to have a theory where God's creation is in the middle of everything, rather than going around the sun, which is then the sun becomes more important. So the church became quite antagonistic to Copernicus's views, and in the time of Galileo, he felt a lot of pressure from the church. At one point, he was arrested. He was shown the instruments of torture. Back in those days, they had the Inquisition. The church was not always a very friendly organization. They would torture you if you didn't ascribe to the views at hand. He was shown the instruments of torture and very correctly said, okay, maybe I'm wrong. So he recanted, but of course, privately, he would have still maintained his beliefs. But in his last years were all spent under house arrest, because the church was still suspicious of his activities and didn't allow him to go out. And he had to smuggle some of his very important works out via relatives and get them published in Holland. There was a bit of intrigue going on there with Galileo. Okay, and then we come to Tycho Brahe, who I think was a Danish astronomer and a very great observational astronomer. And he wasn't exactly so much a mathematician, but he was an excellent observator, an excellent observationist. Is that the right word? He created a fabulous astronomy. He created a fabulous astronomical observatory. I think he was given a large amount of money by a king, and perhaps near Prague, somewhere he had a little island somewhere where he created this observatory. And there he made much more careful observations of the various orbits than had been done up to that time. Very, very careful, painstaking observations of where Mars was every single day, where the moon was every single day, recording exactly where everything was over a long period of time. And his observations became very critical in the important developments of Kepler. So Johann Kepler, was another one of these interesting figures that sort of have one leg in the modern world and one leg in a kind of a mystical view of things. Kepler was a very able mathematician, brilliant mathematician and astronomer, but he also had the sort of mystical side that expressed itself in a number of ways. So Johann Kepler, was a mathematician who was interested in lots of things, but he had a particular interest in the Platonic solids and the Archimedean solids, which are a generalization of the Platonic solids. Let's say and generalizations. So I remind you, the Platonic solids are the dodecahedron and the icosahedron and the cube and the tetrahedron and the octahedron, the 5 Platonic solids. And he also studied more general things where you're allowed to make an object with 2 kinds of faces, not just one kind of face. It's called an Archimedean solid. And he also created other kinds of regular star-shaped objects like that. That turned out to be quite important in his interest in astronomy, because he became an assistant to Tycho Brahe. And was tasked with taking the mathematical observations and trying to make some theory, to try to create some theoretical framework for these astronomical observations. And he did. But he created several theories. So his first theory, which he was very proud of, was a theory that explains the various orbit sizes around the sun. So we have the sun here, and then inside the first planet is Mercury, and then we have Venus, and then there's Earth, and then there's Mars, and then Jupiter, and then Saturn. This is not to scale. So he adopted a Copernican point of view by this time. And the question is, well, how can we explain the relative sizes of these circles? So to Kepler, these were at first just basically circles. They're all pretty close to being circular orbits. And they're all pretty close to lying in a plane. They don't go off in completely different directions. So they're almost all lying on a plane. And the natural question is, what is the relationship between these various radii? And to Kepler, it was no coincidence that there happened to be 6 planets and 5 platonic solids. And he thought this must be connected somehow. And he was able to cook up a theory which these days, it seems like a pure coincidence. But the theory is that the various planets are all on shells. So you kind of have to think of spherical shells that contain each of these orbits. So you have to think of these spherical shells surrounding the sun at various radii. And he explained the relative positions of these shells. Explained by nested platonic solids. So if you have a sphere, you can put a cube inside it. Okay. Or maybe we could say if you have a cube, you could imagine from that cube, there's actually sort of 2 spheres that are naturally associated to it. One is the sphere that circumscribes it, that goes right around the vertices and touches the vertices. And then a slightly smaller sphere that touches the faces, so inscribed sphere. Okay, so you have to imagine these 2 spheres. One is touching or going through the various vertices, and the other sphere inside is just touching the faces. It's a circumscribed and an inscribed sphere in that cube. Okay. So what he said was, if you start with the shell of Saturn, okay, and you put a cube there, so make it the circumscribed sphere of a cube, then the inscribed sphere is going to describe the orbit of Jupiter. Okay, so the relationship between Saturn and Jupiter is given essentially by a cube, which circumscribes this orbit, and inscribed gives this orbit. And then to go from Jupiter to Mars, there's another platonic solid. Maybe it's a tetrahedron. I can't quite remember. So you have to imagine now going from Jupiter to Mars, a circumscribed sphere going through the vertices of a tetrahedron, and then an inscribed sphere touching the faces corresponding to Mars. Okay, and then so that was maybe a tetrahedron. Oh, I'm not sure if I get these right. And then from Mars to Earth was, I think, perhaps a dodecahedron. And then from Earth to Venus was an icosahedron. And then from Venus to Mercury was a octahedron, is the only one left. So the separations between the orbits, the outer 2, all the way to the inner 2, were described by the relative ratios between the circumscribed spheres and the inscribed spheres of the 5 platonic solids. And this fit with the observations very well. Didn't fit perfectly, and throughout his career, Kepler kind of adjusted things and gave reasons why it might not have fitted perfectly, but this was his idea. So it fits very well with the observations. And you could have imagined his sort of joy at having this practical thing about the sky and the motion of the planets connected with these beautiful Platonic solids. So here was sort of a harmony of God's mathematical side and the physical side. He thought about music, he thought about the harmony of the spheres and so on. Okay, these days it's just a strange coincidence that this works. No one takes this seriously these days at all. But Kepler also worked on another problem, which was to have much greater consequences. He also thought about the orbits of the various planets and whether they were in fact actually circles around the sun. And I hope we can appreciate these days, you know, you have this massive observational data from an astronomer that says that on June 11th, you know, Mars was exactly in that direction. And then on June 12th, at some other time, it was exactly in that direction. So you have all this data, reams and reams of data. And from this data, you've got to figure out in your mind where the planet's actually going, taking into consideration that the Earth is going around the sun and the Earth is spinning around its axis while it's doing it. Okay? So to reconstruct the actual model of where the planet is at any given time, it's highly non-trivial mathematics. Highly non-trivial. So Kepler studied the motion or the orbit of Mars. And he had various theories. At some point he realized that it was not quite circular. Okay, it was some kind of ovoid. So this is not exactly the epicycles of Ptolemy that result from having an Earth-centered point of view. This is already when you realize that things are going around the sun. So there's Mars, and it's doing something that's pretty close to circular around the sun, but it's not quite a circle. So it's some kind of ovoid, some kind of more general curve. So what kinds of curves did Kepler have to draw on? Well, one kind of curve that was floating around was a kind of a curve that's been studied from the ancient Greeks. If you take a torus or a donut and you cut it with a plane, like say in this direction here roughly, then you can get a curve which has a sort of an oval shape. Right, this is called an oval of Cassini. That was a candidate. Maybe it's the curve like that. Or another kind of curve is the sort of epicycle kind of thing where you have a circle rolling on another circle. Okay, so maybe you have this circle rolling on that other circle, and you mark a point on it, and it kind of does something like that. But what Kepler eventually realized that the correct curve is a conic. Okay? Or a conic, which algebraically were simpler than these curves because they were given just by a degree 2 equation. And the kind of conic that he realized was going around was an ellipse. And Kepler's first law is that the planets move around the sun in elliptical paths with the sun at a focus. So the sun is actually not in the center of the orbit. It's sort of off to one side. So to exaggerate it a little bit, if here is an ellipse, that's more exaggerated than the planet's orbits, but it would have two foci. Okay, and I remind you that the foci of an ellipse have various nice properties. For example, if you reflect a sound wave there, it bounces off and comes back to the other focus. So this angle is the same as that angle, or this spread is the same as that spread. Okay. So these are the foci of the ellipse. And what Kepler was saying is that if this is the sun, then it's going to be at one of the foci, and the planet is going to go around the ellipse with the sun at one of the focuses. But he was able to deduce more. He was also able to figure out the second law, which is that equal areas are swept out in equal times. Okay, that means there's the sun. If the planet is moving around here, and in 1 month, it say goes from here to here, then the next month it's going to go from here to here, then this area and this area are going to be the same. So if you plot the various months, for example, then what you're going to find is that each one of those segments has the same area. And since this part of the orbit is closer to the sun than this part over here, it means that the planet is going much slower in this more distant area. And it's going faster in this area. So it doesn't go around uniformly. It goes around like this, and it speeds up as it goes close to the sun. And then when it gets far away, it slows down. And the difference depends on the eccentricity of the orbit, sort of how far the sun is away from the center of the orbit. Newton, who explained these laws mathematically, Newton realized that this is essentially equivalent, this second law, to what we now call the law of conservation of angular momentum. To the law of conservation of angular momentum. And then there was also a third law, which is more complicated. So Kepler's third law, let's just say that it gives a relation. It's a relation between the period of the orbit and the average distance to the sun. In other words, orbits which are close, planets which are close to the sun, go around faster than planets which are far away. So these are laws that Kepler deduced by studying the observational record. Kepler did not explain these laws. He just said these are observations, these are the consequences of Tycho Brahe's observations that I have put together. And then we come to the great genius who put this all together, Isaac Newton, who figured out that Kepler's laws really are consequences of very simple, more fundamental laws. Okay? There are yet simpler, more fundamental laws that force this to happen. So Kepler's laws are the consequence of, well, what are now called Newton's laws of motion. Newton's laws of motion and Newton's law of gravitation. And with these laws, he really brought into focus Galileo's idea that mathematics could explain what's going on. And he really sort of found the Holy Grail that people had been searching for thousands of years, to explain in a simple way why it is that the planets do what they do. It's hard to overestimate the importance of Newton's accomplishment here. Okay? This is, in my view, pretty well the greatest accomplishment in the history of science. Okay? And really sets up the modern world. This idea that what's going on out there in the world is not some kind of random, impossible to understand stuff that you can just sort of describe qualitatively. That there are laws which are mathematical that can explain even seemingly complicated things. That seemingly complicated things can be reduced by seeing them in the right way to very simple ideas. Such an important and influential idea that really drove the development of science and mathematics in the next couple hundred years and still going on today. So this had enormous impact on the development of our modern world. So what are these laws, and how did Newton use them? Well, the laws are okay, I'll just say them simple-mindedly. The first law is that unless there's a force, without a force, velocity is constant. So if you have some object which is moving at some velocity, and you don't subject it to any force, then it's going to keep moving at that velocity. It's not going to speed up, it's not going to slow down, it's not going to change direction. It's just going to keep on moving. This is a great insight because it's contrary to what we experience in ordinary life. Ordinary life, you roll a ball, it rolls, it slows down, it stops. You throw something up, it moves, eventually comes down. Everything slows down and stops. But that's because of friction. Friction is a force that's retarding the velocity. But in the absence of a force, velocity is constant. That's what happens, for example, out in space. If you're away from all other objects, a particle is moving. Once it starts moving, it just keeps on going. Okay, very simple but key insight. Second law, that if you do have a force, then you can compute the acceleration in a very simple way. Namely, if you know the force, then the force is proportional to the acceleration. Or it's usually written as an equation, F equals ma. Okay, these are, in fact, vector quantities. So if you have some particle that's moving along, then it's got some acceleration. And the acceleration is roughly, how the velocity is changing. So here the velocity is in this direction, then here, then here. The velocity is changing with an acceleration that's in this direction. And the Newton's law says that we can compute that acceleration if we know the force on the particle. If the acceleration is in this direction, it means that the force is also in this direction. And the constant is the mass. So what we can get at through this law is we can get at the acceleration. If we know the forces, we can get at the acceleration. This is now going to be a basic principle for mathematics in the next couple hundred years, that if you know the forces, then you know the acceleration. And then you can get at the velocity by integrating. You have to integrate to go from the acceleration to the velocity. And if you want to go from the velocity to the actual position, then you have to integrate again. So if you know what the forces are, then you can calculate the position, but you need to do still some more work. You have to be able to integrate. Or as the 18th century mathematicians would have said, you need to solve a differential equation, a second order differential equation, because there's really two integrations that you need to do. The 17th century people didn't think so much in terms of differential equations, but that became very popular once Euler started applying his understanding to this situation. So it really became a second order differential equation. And what about the third law? There's three laws of motion. The third law is that every action has an equal and opposite reaction. Has an equal and opposite reaction. So if I hit this duster, well, that duster is also hitting me. It's not just the duster that's feeling something, my hand's also feeling something. Or if you're stepping off a boat, there you are. You want to take a big step to get up on the land. You take a big step and you go forward. So your motion in that direction is balanced by an equal motion of the boat in that direction. So you're going to go forward and the boat's going to go backwards, and if you're not careful, you're going to end up in the water, as many people probably can attest to. Okay, and then there's the law of gravitation. Which is a very large-scale law that mostly applies to big things. Okay, but in fact it applies to small things too, but the force is sort of small there. But if you have a sun, and if you have an earth, or you have a moon, then the sun and the earth attract each other. Okay, there's a force of attraction due to the attraction of the sun and the earth. And this force is proportional to, well, it's proportional to the mass of the sun and to the mass of the earth, and proportional to the square of the distance between them. So if you double the distance, then the force becomes 1/4 what it was before. If you divide the radius by 2, come up twice as close, then the force that you feel is 4 times what it was before. Okay, and this constant is also important, that Newton's constant gravitational constant. Okay, and so with these laws and his newly discovered calculus, Newton made probably the greatest mathematical calculation of all time. All right, so his calculation is what happens if you have a sun and you have an Earth, and let's say this Earth is at some point, traveling in that direction. Well, if there was no sun here, the first law would tell us that this Earth is just going to keep on going. But the sun here means that this Earth feels a force. That force depends on how far the Earth is away from the sun. If it's far, it feels a small force. If it's close, it feels a big force. And that force, given by this law of gravitation, gives an acceleration to the Earth. It means that the velocity is going to change. Instead of being there a minute later, it's going to be a little bit like that, because the velocity has changed from this to this. The change in the velocity is in the direction of the acceleration. So that a second later, it's no longer going in that trajectory, it's going in that trajectory. And then a little while later, it's going in that trajectory. And eventually, it creates an orbit which is a conic. Newton proved that the orbit is a conic. And he proved that the sun is going to be at its focus. And he proved that the areas swept out in equal times are equal. So he derived Kepler's laws as consequences of his laws of motion and this gravitational law. So the Principia calculated that Kepler's laws are correct. A little bit unfortunately, Newton, who was a great fan of Euclid and ancient Greek geometry, didn't bring the calculus side of this to the fore. Because calculus was this recent innovation that he had made, he realized people may not be that familiar with it. So he wrote it up, putting the calculus a little bit to the side and framing everything in terms of geometry, which made it a little bit maybe complicated to understand. But it's still one of the great works of all time, and this was really the culmination of this long, long history of a problem actually finally being solved. Finally, we know that these things are conic sections, they're ellipses, or sometimes they can be hyperbolas. If we have a comet coming from outer space, and if it's aimed close to the sun and starts feeling the attraction of the sun, then depending on sort of how close it gets, it will be swept out. It will form a hyperbolic orbit, which is actually almost close to parabolic. Most comets are pretty close to being parabolas. Well, when I say comet, I mean a comet that doesn't return to the Earth. There are also the comets that do return. Their orbits are very elongated ellipse, like Halley's Comet. They come back every couple hundred years or every couple thousand years. So most of the time we don't see them. They're often in some far distant part of the solar system, and every few hundred years they come by and they give us a big show, and then they go off again, come back a couple hundred years later. But they're also subject to exactly the same laws. Okay, so it was a great time. People were very excited. They knew they had a lot of power with this new mathematical point of view, and this was certainly one of the culminating achievements in mathematics of all time. All right, next time we're going to have a look, we're going to skip forward a little bit to the 19th century and talk about the beginnings of non-Euclidean geometry. So I'll see you then. So welcome to lecture number 12 in this course in the history of mathematics. I'm Norman Wildberger. We're at the University of New South Wales. And today we're going to talk about non-Euclidean geometry. So we're going to skip ahead to the 19th century, which quite an interesting century. We haven't really talked very much about it at all. We skipped quite a lot from the 17th century where we were last. But this particular topic is somehow a little bit independent of the mathematics that had been going on up till that time. It sort of stands apart from a lot of other developments, and it's possible to tell you about it. It's generally considered a high point in 19th century mathematics, and it's very important because mostly it sets the stage and has great connections with Einstein's special theory of relativity. Well, actually, the general theory too. So Einstein's theory of relativity. Which, of course, is one of the great 20th century developments in science. Now, this particular topic is particularly close to my own heart. I have thought a lot about this subject in the last 10 years, and I have quite a different point of view on it from most of my contemporaries. And so this point of view is going to be influenced today by how I treat this subject. I basically don't agree with a lot of the historical judgments passed in this direction. So I have quite a different take on this, and I'll be honest with you and present the different take on this chapter. This is usually framed in glowing terms. It's one of the great achievements of 19th century mathematicians and so on and so forth. But I think a more sober assessment reveals that there's a lot of confusion and errors that were associated with this development. And some of that confusion and some of those misunderstandings are still with us today in 2011. In terms of modern mathematics, still doesn't understand non-Euclidean geometry properly. And so the physicists don't quite have the right tools to understand their theories. And I want to tell you a little bit about that. So the usual story has three main heroes. And they are Carl Friedrich Gauss, Lobachevsky, and Janos Bolyai. Okay. Now, Carl Friedrich Gauss was the dominant mathematician of the early 19th century. He took the reins after Euler and Lagrange. He was the central figure and made huge contributions in many different areas in mathematics. And he ranks only behind Euler and Newton in terms of the pantheon of modern mathematicians. It was really he who understood the existence of non-Euclidean geometry before anybody else. But for various reasons, he kept it to himself. He was a perfectionist and didn't want to publish anything until it was really perfect. And also, he was a little bit afraid of upsetting the status quo. And so he kept it to himself and never published it. And when Lobachevsky and Bolyai, a Russian and a Hungarian, when they discovered this theory essentially independently around the 1830, it became clear that Gauss had already understood a lot of what they had developed much earlier, but had kept it more or less to himself and to his students. So the story is that Bolyai had a father, Wolfgang Bolyai, who worked on geometry and worked on this famous problem of Euclid's fifth postulate. That's the parallel postulate. And I remind you that in the beginning of Euclid, he posits 5 things that we should assume that are obviously true. And the fifth one, which is a little bit more complicated than the others, asserts that if you have a line, and if you have a point that's not on the line, then there's exactly one line which goes through that point, which is parallel to the given line. And parallel means that it doesn't meet that line. There's exactly one line through that point which doesn't meet the given line. Now, to say that requires more words than any of the other postulates. The other postulates are things like, if you have any 2 points, you can always draw a line between them. If you have a line, you can always extend it a little bit further. If you have a point and a radius, you can always draw a circle. And that all right angles are essentially the same. Those are the 5 postulates. And these other 4 are reasonably easy to describe, but this one is more complicated. And people try to prove this postulate from the other 4. That was a popular thing to try to do. That goes back to Arab mathematicians were interested in doing that. And there were a whole host of people in the 1600s, 1700s, 1800s who tried to prove Euclid's 5th postulate from the other ones. And it was from this attempt that non-Euclidean geometry was born. Non-Euclidean geometry was the result of thinking that perhaps this postulate couldn't be proved from the other 4. So it was the opposite direction of what everybody else was trying to do. And Gauss was the first to really realize that this was a possibility, that it might be possible to have a geometry that's just like Euclid's geometry in the sense that these other 4 postulates are working, except that there might not just be one line through a point that doesn't meet a line, but there might be a whole range of points, or there might be a whole range of lines through a given point that don't meet a given line. There might be such a geometry. And how exactly this geometry should look was not entirely clear. But both Bolyai and Lobachevsky and Gauss started developing this geometry and seeing what the consequences of adopting this postulate are. So the new postulate is there is more than one line through a point, say A, not meeting another line, L. Now, the people who had preceded Gauss, and there's quite a whole host of them, they had tried to contradict the 5th postulate and to try to find a contradiction. So they knew that there were a couple of equivalent things to the negation of the 5th postulate. I'll come back to these other people later. So earlier researchers knew more or less that the parallel postulate, let's call it PP, the parallel postulate is really equivalent to, or pretty well equivalent to, a host of other statements. In particular, to the statement that the sum of the angles in a triangle is 180 degrees. Or 2 right angles, as Euclid would have said. So in order to prove that, Euclid had to use the parallel postulate. And eventually it became clear that the parallel postulate was really kind of equivalent to that statement. Another statement that it was equivalent to was the idea that there are similar triangles which aren't congruent. There are similar triangles which are not congruent. So we all know that maybe that triangle there is maybe similar to this one. The angles are the same, but the sides are different. And that turns out to be also equivalent to the parallel postulate. And there were others like this. And at some point, the arguments would have gone, well, we reduce the parallel postulate to some other statement, which we think of as sort of obvious, and then say, well, therefore, the parallel postulate must be true. Because it's obvious that there are triangles that are similar and not congruent. But Gauss realized that you couldn't really argue this way, that it might be that there is some weird geometry in which all of these statements are not true, which the parallel postulate is not true, which the sum of the angles of a triangle is not 180 degrees, which there are no similar triangles which are not congruent. So Gauss worked on this sort of strange geometry, didn't quite know what it really was about. And then Bolyai, who was the son of a friend of his, worked on it, even though his father pleaded with him not to waste his time on this. Said this is a black hole of endless toil that will not get you anywhere, because his father had spent years working on it too. And then in Russia, this fellow Lobachevsky also worked on it, and Bolyai and Lobachevsky, roughly around the same time, around 1830, Lobachevsky was actually first. Bolyai and Lobachevsky published sort of consistent accounts of this non-Euclidean geometry, where they assume this new parallel postulate, or the opposite of the parallel postulate, and show that there's a kind of consistent geometry that can be built up from it. So published this new non-Euclidean geometry. So they were both very courageous, and they were both very insightful. They were geniuses. Okay, they really deserve a lot of credit, because they went out of their way. They saw a new world, and they were not afraid of venturing out there and figuring out what's going on. But the story is really a sad one, okay, because even though they did this remarkable work, they were ignored by their contemporaries. Their contemporaries couldn't understand what it was about, and they uniformly ignored both of their works. Now, the young Bolyai was very dismayed by that. He was also very dismayed when his father wrote to Gauss, who was a friend, and told him about Bolyai's achievements. And Gauss wrote back a very famous letter that says, well, that's all very good, but unfortunately I knew all of this 20 or 30 years ago. So that really devastated Bolyai. It's probably not true that Gauss knew all of that. He was probably exaggerating a little bit, but certainly he would have known the general thrust of it. So Bolyai was discouraged, and eventually sort of gave it all up, did other things. And Lobachevsky was working in a very small provincial town called Kazan, somewhere in the Soviet Union. And he didn't have a lot of support, but he kept on working. It didn't faze him too much, and he kept on going and developing his theory. Ultimately, Gauss learned about Lobachevsky's work, and the story is that Gauss purposely learned Russian in order to understand Lobachevsky's work on this geometry. Okay, so now I want to tell you, well, what is this geometry actually? All right. And here's, I guess, where I have quite a different point of view on things. But I think that this is a sad chapter in many ways. But one of the reasons it's sad is because people really there was this very easy opportunity to discover non-Euclidean geometry years and years before, and it somehow had been ignored. People got sidetracked by Euclid's 5 postulates. Instead of just asking, what's the natural thing to do? What should we really be doing here? It's hard for us to imagine how important Euclid was to these people. It was like a Bible. It really was like a religious text. So if Euclid said there were 5 postulates, then there were 5 postulates. You know, it wasn't a matter of opinion. They really took it completely literally. And unfortunately, they took it too literally instead of thinking, well, what's really going on here? If they had asked what's really going on here, they would have realized that there was a non-Euclidean geometry right in front of their nose, and it had been for millennia. Okay. There is another non-Euclidean geometry. In fact, arguably, it's the most important geometry historically. What's that? That's the geometry of a sphere. The geometry of the surface of a sphere. That is also a non-Euclidean geometry. It shares many similarities with Euclidean geometry. You can still talk about points. You can still talk about lines. You can still talk about triangles. You can even talk about distances and angles if you want. You can talk about areas. You can talk about proportions. This is in the proportion 1 to 2. And in fact, this kind of geometry had been studied for millennia. Ptolemy had studied this. All the astronomers were more interested in spherical geometry than they were in planar geometry because, as I've mentioned many times, the night sky is obviously a sphere. What goes on in the night sky is really happening in the celestial sphere, and so this is obvious that the sphere was important. So the ancient Greeks, the Indians, the Arabs, everybody had studied spherical geometry. It was an obvious non-Euclidean geometry. Why didn't they consider it a non-Euclidean geometry? Well, because it doesn't quite fit Euclid's 5 postulates. Why not? Is it true that if you take any 2 points on the surface of a sphere, there's a unique line joining them? Well, what is a line, actually? A line in this context is like a great circle. Okay. The lines are great circles.